Well, you could like like what call this something
Okay, let's get started with today's class. So we're gonna finish the notes I handed out last week, which is focusing more on like the theory around singular value decomposition. Does anyone need the notes from last week at all? We're kind of like on the last couple of pages. There's really two more things I want to go over. Like everything kind of a sort of going on with this stuff. And then we'll go through an example where we actually find the singular value decomposition. And then after that, we're going to go into some applications of singular value decomposition. So we're going to be looking at principal component analysis, which is a major idea in data science, which involves dimension reducibility. So it's like we're going to look at an example where we're looking at a number of different indices or like indexes in finance. It's going to be like 9-dimensional data, and that there's going to be like 9 time series. And then we're going to see that you can really understand it pretty well by reducing it to just a single dimension, which is going to make it a lot easier to understand. And this is really just going to be done by using singular value decomposition and applying it to what's called the matrix of covariance. So that's what we'll be going into today. So I'm going to briefly review what we've been talking about already. I've done this a couple of times, but it's an important idea, so I guess it's worthwhile. And so we've been looking at singular value decomposition. It's kind of like diagonalizability, like we've seen before, except it works for matrices that aren't necessarily going to be square matrices. And so we're going to be taking any matrix A and then writing it as the following product. So this is U, sigma, V transposed. We talked about some of these matrices already. So U and V are going to be orthogonal matrices, and then sigma is going to be a matrix of the following form. It's going to be an M by N matrix that's diagonal, where the diagonal terms are called the singular values, which are really just square roots of eigenvalues. So we've gone through a couple of proofs on the next page. Like the reason why we can define the square roots of eigenvalues is we show that if you have a matrix of the form of A transpose times A, then it forces the eigenvalues to be greater than or equal to 0, which means that the square roots are going to be defined. And so the general idea is you take your eigenvalues, you order them from the largest to the smallest. So it's kind of like the most influential in terms of the direction you're going into, given an eigenvector, to the least influential, which is a perspective we'll have later on today. And you take the square roots, these give you the singular values. And we show that this number of singular values of A ends up being equal to the rank of A, or I should say the number of non-zero singular values ends up being equal to the rank. And so where we left off, so that gives us some good information about singular values and eigenvalues and stuff like that. Where we left off is we were showing how to go from eigen decomposition or diagonalization to singular value decomposition. The connecting idea is you're really just applying eigen decomposition to A transpose times A. That was kind of this derivation that we did here. So if you do the diagonalization of A transpose times A, you can write it in this way, where V has column vectors that are given by the eigen, or has columns given by the eigenvectors of A transpose times A. This is a symmetric matrix, so the eigenvectors are going to be orthogonal to one another, which then you can reduce to orthonormality, so you can make it so all the columns are orthonormal. And then you have all these various reductions. So this is what we did. You can write sigma as really the square, or lambda as the square of sigma. U transpose times U is orthogonal, so this is just going to be equal to the identity. And then you can rewrite all this, so that way it's this matrix multiplied by this matrix, which is kind of like having A transpose times A. Right, so that's kind of where these matrices U, sigma, and V come from, is really just the diagonalization of A transpose times A. And so the final kind of observations to make before actually going through with an example where I give you a matrix and you have to find the SVD. And so in order to have the SVD equation A is equal to U times sigma times V transpose, if you multiply both sides by V, this implies that we have A times V has to be equal to U times sigma, which column-wise then means that we have to have that A times the ith column of V is equal to sigma times the ith column of U. So it's kind of like you have
well, it's not really like an eigenvector, but it kind of looks like an eigenvector almost, except this vector is changing from V to U. And we're going to assume these columns are still going to be unit vectors by Gram-Schmidt. And so the main observation is that because the V vectors are going to be orthogonal as eigenvectors of a symmetric matrix, it's going to force the U's to be orthogonal as well. Therefore, U is going to be, well, you can make it so they're going to have unit length, which is then going to make it so it's going to be orthonormal. So we need to prove that the U's are actually going to be orthogonal to one another. So the idea is this. We just need to show that if you do UI dotted with UJ, it's going to be equal to 0. So we're going to assume, and this is when I is not equal to J. So we're going to assume is I is not equal to J. And we're going to look at the dot product of UI with UJ. So this is another way of writing the dot product. We've done it a number of times in this class. And so using this equation here, we can write out the UIs using A, VI, and then sigma as well. So that's really going to be the main observation here. So you can rewrite this using this equation by dividing both sides by sigma to say that we have that A, VI over sigma I transposed is going to be multiplied by A times VJ over sigma J. Right, I'm just using this equation to rewrite the UIs and the UJs. And then we'll use the orthogonality of VI and VJ to make this kind of work out here. And so you can rewrite this in the following way. We can apply the transpose to this equation here, which is really going to influence just the numerator. And so this is going to be equal to VI transposed times A transposed, and then you have A times VJ in the numerator. And then this is going to be over sigma I and sigma J. And so we can make use of the fact that by definition, this matrix V has column vectors that are going to be the eigenvectors of A, or of A transpose times A. And so if we have A transpose times A times VG, or not VG, VJ, again, this is an eigenvector of A transpose times A. Right, so you can write this as really a scalar product of Vj. And so this is going to end up being equal to Vi transposed. This part here, you can rewrite either as like a lambda J times Vj, or you can write it as, in terms of sigma, as sigma J squared times Vj. And then this is going to be over sigma I, sigma J. Again, we're making use of the fact that Vj is an eigenvector of A transpose times A. And so if you square this sigma, by definition, that just gives you the eigenvalue, because the singular values are just the square roots of the eigenvalues, so you can always write it out in this way. And so, I mean, it doesn't matter how you write it out. What really matters is you have some constants. You have sigma J squared, and then you have sigma I, sigma J. What really matters is you have V transpose times, or Vi transpose times Vj. So this is the dot product of Vi and Vj, where we know these vectors are orthogonal as eigenvectors of a symmetric matrix. So this ends up just being equal to 0, and so the whole thing becomes 0. So because the columns of V are going to be orthogonal, it forces the columns of U to be orthogonal. So it turns out U and V both end up being orthogonal matrices. Okay, any questions about this derivation here, like any step of it? Yeah, so this is kind of like the key value in being able to recognize, like, when you have eigenvalues and eigenvectors, is you don't have commutativity with matrices, so you can't just like take this out in front and then assume you can multiply these things. But because we can write this product as a scalar multiplication, it allows you to move things around a lot easier. So that's the value of the eigenvalues and the eigenvectors in a lot of situations. Okay. Any questions? Okay. And then the rest I just put into words, right? So we didn't really go down this route, but you could have gone down a different route. Like, we've been looking at A transpose times A. You could also start with A times A transposed, and it turns out that these U's are going to be the eigenvectors of A times A transposed. And then you can use that to derive what the V's are going to be. It's the same kind of thing at the end of the day. And so to finish the construction, we're going to make use of an observation we made before. So there's a couple of observations here. So we note that the number of U's and the number of V's that we currently have is equal to the rank of A. Right, they are determined really by I guess like the number of orthogonal eigenvectors you had, so it like forms a sort of basis. So they currently are equal to the rank of A, which we're going to say is going to be equal to R. And so there should be a space here. So using the RVs that we have, not like R times V, there should be a space here. So using the RVs that we have, you can complete a basis by then adjoining. So this is going to give you the V's here. So the V's here were the, sorry, I'm like blanking a little bit. They're the eigenvectors of A transpose times A. And we know that the null space of A transpose times A is equal to the null space of A. And so I've said before, really what these V's are going to be giving you is if you think about their column space and then you take their transpose, it's going to give you a row space that's going to end up being equal to the row space of A, right? So like we're going to be using the fact that like this null space of A is really equal to the null space of A transpose times A, which then implies that the row space of A transpose times A is equal to the row space of A. So you can use these R V's that we have, that fills out these first R rows, and it's really just going to be the row space of A. And then to complete this n by n matrix, you can adjoin other vectors that are going to be orthogonal, right? So you take the row space vectors and then you add in the null space vectors. We know those spaces are orthogonal to one another. And so that will complete a basis that you use to fill in V transpose. So V transpose, again, is just the row space of A and the null space of A due to the fact that these two things are equal to one another. So like these added vectors, VR1 or V of R plus 1 to Vn from the null space of A form an orthonormal basis of the null space. And then you can do the same thing with U. So from another perspective, you can think in terms of A times A transpose. These vectors will give you a basis of the column space that ends up being equal to the column space of A. And then you can fill out a basis of M vectors by then adjoining to that the basis to the left null space, because we know these spaces are going to be orthogonal to one another. Right, so you end up getting the following decomposition, right? So even though like I've always been doing things in terms of A transpose times A and A times A transpose, from this perspective in the picture here, it all reduces to the four major subspaces of A at the end of the day. Right, so there's kind of like the eigenvector interpretation, which is what I use more frequently. But you can also come up with these matrices by just finding a basis for the column space and then adjoining to that the orthogonal complement, which is the left null space. And then you have a matrix consisting of the singular values. And then this V is going to consist of a basis of the row space of A. And then you complete the basis to get an m by n matrix by adjoining a basis for the null space. Right, so there's a couple of ways of thinking about it, but this is one way of thinking about it in terms of the four major subspaces. Right, so it's kind of a lot. We spend a lot of time talking up like where this theory is coming from, like how the decomposition works, and we'll work through an example here shortly. But at this point in time, it's really just a matter of recognizing some of these things, right? So these like U1 to UR, where R is the rank. I'm just repeating myself over and over again, I feel, but it's like basis for the column space. Then you have the complement, which is a left null space. V consists of the row space and the null space, pretty much. So it's just what I've been saying. And then this perspective here will come in handy later on today when we're doing principal component analysis. So like the components of principal component analysis are really these sums right here. What's going on with this singular value decomposition, another interpretation of it is you're taking your matrix A, which you can then write as this product here, which you can really represent as this linear combination of the columns of U and the rows of V, and then like some sort of singular value. And again, we order the singular values so the largest ones come up first and the smallest are least. So in terms of understanding A, the most influential of these sums is going to be the first one here, and then the second one, and then the least influential is going to be this part right here. So like eventually we'll be able to analyze like markets and say like we only need one or two of these sums to understand what's really going on with the entire data set. We don't need to care about like this final sum here. So when I'm talking about components later on, I'm really talking about these sums. Right. So these are the components, and they're really associated to the eigenvectors you have, right? So this is like the eigenvector of A transpose times A. So this is like the component associated with like this eigenvector. So that's usually the sorts of terminology people would use. So we'll go back to this later on. But before doing that and going into applications, I want to go through one example. There's going to be a homework problem, or there is a homework problem where you have to find these sorts of matrices, and it really isn't so bad. Again, it mostly just boils down to finding the diagonalization of A transpose times A. And so we have this matrix A given by 3, 0, 4, 5, and it wants you to find the three parts of the singular value decomposition. And so maybe I don't have to write this down, but I'm going to anyway. So I'm going to say that A has rank 2. Right, it's a lower triangular matrix. The diagonal has non-zero terms. So you have 2 pivots, which means that it has rank 2, which then implies that we're going to have 2 singular values. Right, we know the number of singular values is equal to the rank of our matrix. And so I'm going to go about this through the perspective of eigenvectors and eigenvalues rather than just finding what the 4 major subspaces of A are going to be. And I think it actually goes a little bit faster. It depends on the difficulty of the matrix, I suppose, but there's a lot of calculators that work efficiently for finding eigenvalues and eigenvectors. So it's usually pretty safe to go this route. So I'm going to find A transpose times A, and then I'm going to diagonalize it, and that will give us information about sigma and V immediately, and then you can use sigma and V to determine what U is going to be equal to. So A transpose times A, if you do this multiplication, so this is 3, 4, and then it's going to be 0, 5. This is going to be multiplied by 3, 0, and then 4, 5. If you perform this multiplication, you get the following symmetric matrix given by 25, 20, 20, 25. And in the solutions, I'll write out like what A times A transpose is going to be. But we really just need to think about A transpose times A. You can derive everything from A transpose times A. And so what ends up happening is you want to diagonalize this. So you want to find the eigenvalues and the eigenvectors here, which these are pretty big numbers. So you would want to put it into a calculator, or you can reduce it by factoring out like a, well, even factoring out a 1 over 20. I mean, if you factor out like a 1 over 5 or something, it would make the numbers a little nicer. But what ends up happening is you have eigenvalues given by lambda 1, which ends up being equal to 45. If we have lambda 1 is equal to 45, that means the singular value is just the square root. So that's going to tell you that sigma 1 is equal to the square root of 45. And then the other eigenvalue is lambda 2, which is going to be equal to just 5, which implies that sigma 2 is equal to the square root of 5. Once you have the eigenvalues, you want to determine what the eigenvectors are going to be. So the corresponding eigenvalues or eigenvectors, and it should be worth noting that these are ordered from largest to smallest. That's the practice when you're doing singular value decomposition, is you always want you order the indices based on the size of the values. And so the corresponding eigenvectors aren't too hard to find once you find the eigenvalues. So it ends up being 1, 1, which I'm going to normalize. So I'm going to make it so it has unit length. So I'm going to let Q1 be equal to 1 over the square root of 2, and then you have 1, 1. And then the eigenvector corresponding to lambda 2 is going to be V2, which is going to be equal to minus 1, 1, which if you make into a unit vector, it's going to be 1 over the square root of 2, and then you get minus 1, 1. Right, and you should notice that these vectors are orthogonal to one another. They're eigenvectors of a symmetric matrix, so they're guaranteed to be orthogonal. Well, they also have distinct eigenvalues, so it's going to make it so that works out. And so this tells us what V is going to be. So to get the matrix V in the singular value decomposition, you take Q1 and Q2, and then you just make a matrix out of them. Right, so we have V is equal to 1 over the square root of 2, and then you have 1, 1, and then minus 1, 1. And then we also have sigma as well. Right, so we have sigma is a diagonal matrix consisting of your singular values. So we have 1 is equal to the square root of 45. Oops. So you have 1 is equal to the square root of 45. And then the other is equal to the square root of 5. And so we already have 2 of the parts just from doing this process. And again, it is a little like I would use a calculator to find this. I just used the book and took the numbers from the book, but if you didn't have a book to look at, you can use a calculator to find these eigenvalues. That'd be kind of annoying to find otherwise. But after finding the eigenvalues, the eigenvectors are easy to find, and then you just use what you know to put these two things together. So like 2/3 of the way done already. Okay, any questions so far about V and sigma at all? Yeah, and then once you have V and sigma, it's not so bad to determine what U is going to be equal to. So the singular value decomposition guarantees that we have that A is equal to U times sigma times V transpose. We know what A is, we know what sigma is, we know what V is. So you can move these terms over to the left-hand side and then solve for U through matrix multiplication at this point. So if you multiply both sides by V, that'll tell you that A times V is equal to U times sigma. Again, V is an orthogonal matrix, so the transpose of V is equal to its inverse. So if you multiply V transpose by V, they cancel out with one another, which is why there isn't a V on the right-hand side. And then we have that sigma. In this case, it's a diagonal matrix. It's invertible. So you can then write that this is going to be A times V times sigma to the -1 power is equal to U. So it's just a matter of computing this matrix product, and that'll tell you what U is going to end up being equal to. And so this is going to give us the following. So I'm just going to do A times V times sigma inverse. So A is equal to 3, 0, 4, 5. We had V was equal, so I'm going to bring this 1 over the square root of 2, and then you have 1, -1, 1, 1. And then multiplied by sigma to the -1 power. Sigma to the -1 power is just taking these numbers and then doing 1 over. So you take the reciprocal. So this is going to be 1 over the square root of 45, 0, 0, and then 1 over the square root of 5. And if you go through with this multiplication, there's a couple of steps that, I mean, the multiplication is kind of ugly because you have a bunch of square roots running around. But you end up getting the following. So this ends up being multiplied. If you multiply everything, you end up getting this is 1 over the square root of 10. And then you get 1 minus 3, and then 3, 1. And this is going to be equal to our U. Right, so this was our A. This was our V. This was our sigma inverse. If you multiply them all together from this equation, you end up getting U. And so this tells you all the information, right? So this would end up giving you, the columns give you a basis for the column space up to like rank 2, which this is just like a 2 by 2 matrix. So there's not like a null space that shows up anywhere, but this would give you like a basis for the column space of A. So you can read off the column space here. You can read off the row space here. You can read off the eigenvalues here. It gives you like all the information you would want pretty much. Right, so this is what you have to do, or this is one way of going about things. There's a number of other ways, but I think this way is not too bad, right? It's mostly just finding the eigenvalues and then just doing diagonalization. Okay, any questions about this example at all? Yeah, question. Oh, yeah, this is from the fact that, like the reason why, so A itself isn't symmetric, but like when we're doing these like singular value decomposition, we're always looking at A transpose times A. This is a symmetric matrix, and what we learned about symmetric matrices is that their eigenvectors are going to be orthogonal to one another. So like V1 and V2, if you take their dot product, you end up getting 0. So they're going to be orthogonal. And then if you make it so they're orthonormal, so you make it so they're unit vectors, what we showed before is that if you take an orthonormal basis and you make a matrix out of it, it's then going to be an orthogonal matrix. And then the definition of an orthogonal matrix is just the fact that like for it to be orthogonal, you just have to have that Q transpose is equal to Q inverse. Like this is what it means to be orthogonal as a matrix. So there's orthogonal vectors, which is when you have vectors that have like a 90-degree angle with one another. And then there's a notion of an orthogonal matrix, which is when the transpose is equal to the inverse. which just means that your column vectors are orthogonal and their unit length pretty much. Does that answer your question? Yeah, other question.
Since it's like a pseudo diagonalization, does this also satisfy the property of like, if you were to raise the singular values to a power or something, does it have like the same effect?
It's not, yeah, it's not going to have the same effect. And as you go through with this computation, like if you did like a to the kth power here, or if you just did like a squared or something like that, we don't have to do like the full thing. This is going to be u times sigma times v transpose times with like u sigma v transpose. So we don't have this nice property that we had before where this term and this term would cancel out with one another. Because this is going to involve, again, like the row space of A and the null space of A, and this is going to be like the column space of A and the left null space. So there isn't really like a lot that's relating the two at the moment. So there's no reason to kind of expect good things to happen. Any other questions? Okay, yeah, so that's it for those notes. There'll be a problem on the homework. You have to do something similar to this. Now we're going to go on to applications of singular value decomposition. And depending on, I mean, there's only about 2 weeks left of class, really. I mean, there's 2 weeks and then there's like a Monday. It's a little bit awkward. So we'll see how far I go into application how soon, but I want to go into other applications beyond this as well. I feel like I have to talk about the fiction for me left a little bit, so we'll see how far I go.
College or high school?
Masters.
I thought you want to.
Oh,
Get two.
Let's go.
What in the world is happening? See, they're adding scenes to.
Anyone need this? Or you want to get a copy?
Me too. Having said that. Can't do that.
Okay, yeah, so we're going to be looking at applications of singular value decomposition. Again, I did like a couple of, I guess like miniature projects over the weekend just to like illustrate some of these ideas. They're really just exercises from like a particular book. All right, can we quiet down? Yeah, so again, this is really the, I guess, projects or the things I was looking at come from this book. I mentioned it before, but there's like practical linear algebra for data science. I might put a PDF on the Canvas so you can go along with it, but you pretty much know everything in this book at this point. Like this is the very last section of the book. So if you wanted to, you can go through it. If you learned a little bit of Python, you can probably do most of the examples and exercises pretty easily, I would say. And so they wax pretty poetic about eigen decomposition and singular value decomposition here, where they call it the gems that linear algebra bestowed upon modern civilization. It's really a matter of perspective, though, in the sense that like what will be, I mean, it's like recommendation systems for like Netflix or like the YouTube algorithm, and then like eventually we'll be going into like facial recognition using like eigen faces. So it's kind of like, well, I don't know. Like, there's good aspects and bad aspects, but we'll go into that kind of stuff. And so we're gonna go into like two applications. Really, they're both centered around this idea of like principal component analysis. So there's gonna be two applications that we'll see. Probably in like you'll probably see principal component analysis. If you do data science, you'll know about it. And then there's gonna be other things in related fields. And so kind of like, I don't know if I'll get to the projects themselves or like the kind of applications that I did. But first we're going to go into like some of the prerequisites first, because we haven't really had like this understanding of like matrices and relating them to data all that much. But the correlation or like the way they relate to one another is pretty simple, right? Like if you have any sort of Excel sheet that consists of numbers, or even if it consists of words, there's like a way of working around that as well. But if you just have like an Excel sheet of numbers, at the end of the day, that's just going to be some sort of matrix, right? So if you're given a collection of data consisting of n observations, which are like samples, and p variables, which are usually denoted as the features, you can form what's called an m by p data matrix X, where each row is one observation and each column is going to give you a variable. So if you look at this, this is kind of like a really cliche data set where it gives you a bunch of flowers and it tells you various information about like their petals and I don't know, like their stem or something like that. And from there, it wants you to be able to classify like what kind of flower it's going to be. So like every single one of these rows corresponds to a unique flower or like a plant. And then every single column, so that's like an observation. So every single individual plant is an instance of like an observation. So they're like unique from one another. They have different measurements. And then each column serves as a variable. So every column, like this one, corresponds to sepal length, sepal width, petal length, petal width. So every column corresponds to a variable or something you can use to measure what this flower or what this plant is going to look like. And then the class is just telling you exactly what kind of flower or plant it's going to end up being. So we see there's 3 classes here. And in the data set, there's only 3 that they're looking at. It's one of like the simplest. Like if you do like a machine learning or data science class, you probably have seen this data set before. Right. And so this is so given a table of this form, you can form a matrix. These are really just numbers. So you can do row reduction on this matrix to try and determine like what information about the matrix. Usually these aren't going to be square matrices. In fact, usually they're going to have a lot more rows than they're going to have columns because you can read in data that has like a million different observations in it, but there might only be like 4 variables, which would be like in a 1,000,000 by 4 matrix. So you have to, they're usually not going to be square matrices. So we're really going to be looking at correlation and really covariance, I suppose, which is the numerator of correlation. And so given a data matrix, one is often interested in finding potential correlations or a correlation between 2 different variables. And so a correlation coefficient is just going to be a single number that quantifies the linear relationship between 2 different variables. And so these correlations are really just saying how much 2 variables relate to one another in a sense. So these correlation coefficients range from -1 to +1, where -1 indicates a perfect negative relationship and +1 indicates a perfect positive relationship. So if one variable is increasing, the other variable is guaranteed to increase as well. There's going to be examples on the next page that we can look at. And then if you have a 0, it indicates that there's no linear relationship whatsoever. So this is illustrated on the next page. This would be an instance of having positive correlation between a variable x and a variable y. So you kind of have this line, which is like the line y is equal to x almost. So pretty much it's saying whatever is happening to x, as x increases, we have that y increases pretty much. So whatever happens to x happens to y. So to understand y, it suffices to just understand what's happening to x. You don't have to look at both of them at the same time. And then even if it's like a negative correlation, you can still understand it, like from understanding x, you can still understand y. It's just like inversely in a sense, in that if x is very high, it must mean that y is going to be very low. So you can still determine what's happening with y with just understanding x. And then these other pictures, it doesn't seem like there's a clear relation that exists between the 2 variables. So we're just going to say there's no correlation whatsoever between the 2. And so if you wanted to compute the correlation that exists between 2 variables, x and y, which in this case we can view as being 2 columns of our data matrix, one can calculate the following. So again, like when we're doing these correlations, we're seeing if this variable could say something about like this variable or something like that. So like these x and y's correspond to like the columns of a data matrix. And so the formula for correlation is given by the following quotient here. It looks really bad because you have like sums and you have like this stuff and square roots and stuff like that. But the first thing we're going to do is we're going to translate this equation into something that looks a lot easier using things that we already know. And then we're going to extend those ideas to linear algebra. So here, this x bar and the y bar is really just the mean of whatever the column is going to end up being. So you take the sum of all the entries in the column and you divide by really the number of observations you have, I suppose, and that'll give you the mean of x. And then you can do the same for y bar here. So this is like having mean-centered data in the sense that you take your original numbers, you subtract by the mean to make it so the numbers are a little bit nicer. There's going to be a number of other tricks we'll look at to make data look a little bit nicer as well. So the first example here is we're looking at this correlation coefficient formula row from the previous page. And we want to rewrite it using a certain vector operation that we've used a number of times in this class. Does anyone see like what vector operation I'm talking about. Like, what is this? What are we really making use of when we're writing out this long equation? Yeah, Andrew. Yeah, these are just dot products pretty much, right? Like we're doing some I component of a vector times an I component of another vector. And then in the denominator, we're really finding the magnitude of vectors, right? So you can think about this in terms of a dot product and this in terms of a dot product as well. So what I'm going to do is I'm going to let x tilde be equal to the following vector. It's maybe a weird way of writing things out, but I'm going to write it as xi minus x bar, where we have that I ranges from 1 to n. So this is just a way of describing all the components of the vector. So when I is equal to 1, the first component would be like I1 minus x bar. When I is equal to 2, the second component would be like x2 minus x bar, so on and so forth. And I'm going to do the exact same thing for y as well. So I'm going to let y tilde, this is going to be equal to yi minus y bar, where I is going from 1 to n. And so we can really think about this in the following way, right? So we can rewrite what I have written here. So the numerator itself, this is really doing the ith component of x bar multiplied by the I component of, not x bar, of x tilde and y tilde. So this is going to be equal to the sum, where you're doing the ith component of x tilde multiplied by the ith component of y tilde. And then in the denominator, you have the square root of the sum of x tilde squared. And then this is times the square root of the sum of y tilde squared. And so you can think about this in terms of dot products. I should have written more space out. Maybe it's not a problem for you, but I use I don't know, my writing's a little bit large. So like this is by definition just the dot product of x tilde and y tilde, right? So the numerator, this is equal to x tilde dotted with y tilde. And then in the denominator, you can express it in terms of dot products, or you can just express it as like the magnitude of these vectors. So I'm just going to say this is divided by the magnitude of x tilde times the magnitude of y tilde. Right. So this is one of the nice aspects of the dot product is this is a really ugly looking equation initially, but you can write it in this very concise form just by thinking in terms of dot products, right? So it's just doing a dot product divided by the magnitudes of the two vectors. And that'll give you the correlation between the two variables. So it really isn't a bad computation. I haven't written the final. I don't know if I'm going to put this on the final, but I'm just saying like it could be something I ask on the final. So it wouldn't be that bad. Any questions about this derivation at all? It actually be kind of annoying because you had to find like x bar and y bar, I guess. But anyway, so this kind of goes back to what we were thinking about in terms of linear algebra in the first week, right? We had like the vector, we had like the dot product between two vectors was in the first week. And then one of the first ways we went from vectors to linear algebra is we were really taking the dot product and extending it to this notion of matrix multiplication. And so we can apply this idea to the correlation coefficients as well, because you might have more than two variables. You might want to know like the correlation that exists between, I don't know, like n many variables. So you can have like a matrix whose entries end up giving you the correlations. And so instead of thinking in terms of correlation, I'm just going to focus on what's going on in the numerator, because you can see in the denominator, we're really just finding a number and then we're scaling it based on like the magnitudes of the vectors. So we really just need to understand what's going on with this dot product. Is it going to be positive? Is it going to be negative? How positive is it? How negative is it going to be? When you're doing the correlation, I should have said this before, the values. Oh, I did say this before. It goes from -1 to 1. This is due to the fact that you're multiplying by 1 over the product of the magnitudes. That makes sure that it's going to be between -1 and 1. And so instead of looking at correlation, we're going to look at covariance, which is just the numerator of rho. So that's just focusing on really this dot product up here. And so there's some data science stuff that comes into play. They say like covariance has a normalization factor of n-1, where n is the number of data points or observations that you have. And so the equation of covariance is it's going to be this dot product divided by like this n-1. And so the key insight to implementing this formula for multiple variables is really just going from the dot product and extending it to matrix multiplication, right? And going from matrix multiplication or going to matrix multiplication, it's really just a collection of various dot products between rows of the left matrix and columns of the right matrix. And so what I'm saying is that this matrix product given by X transpose times X, this represents all possible dot products that you can have between these variables like X and Y. So if you have this matrix X transpose times X, it encodes all of the pairwise covariances, assuming the columns are mean centered when dividing by n minus 1. So the ijth element in the covariance matrix ends up being the dot product between data features I and j. And so what we end up getting is that this covariance matrix is given by C, it's denoted by C, and it's really just going to be X transpose times X, where X is going to be your data matrix, right? So you should be thinking like this is rather nice, right? Because when we were doing the singular value decomposition, we were really looking at like the eigen decomposition or like the diagonalization of matrices of this exact form, pretty much. So like the covariance matrix is always going to be symmetric, which makes sense from its definition. It should be a symmetrical matrix, but it's going to have like real eigenvalues. We know that already. The eigenvectors are going to be orthogonal to one another. So this covariance matrix tells you it has like a number of really nice components. And then from here, we're going to focus on the covariance matrix. But we started off by talking about correlation. So you can go from covariance to correlation via multiplication by diagonal matrices consisting of standard deviations. We're not going to make use of this really at all. But just to be complete, you can get this correlation, which is this product where C is the covariance, and you multiply by this diagonal matrix here. So it's like square root of the diagonal of your covariance will give you the standard deviations. Right, so that's kind of the idea behind like the covariance matrix. And so when we're doing principal component analysis, I might show some of like the example that I did on Python, rather than just talk a lot about principal component analysis and going into the theory. But I'll say a little bit about principal component analysis before going into like what's on the computer or on my laptop. And so what principal component analysis is really going to be, like I'm going to say a lot of words that doesn't sound like it involves linear algebra, but what it really ends up being is it ends up just being the diagonalization of X transpose times X. Like if you're doing principal component analysis, 90% of it is just applying eigen decomposition to this, right? So you find the eigenvalues and the eigenvectors, and then you can interpret it in terms of like singular value decomposition. And it really is going to tell you like what eigenvalues and eigenvectors give you like the most significant contribution to understanding the data that's given to you. So maybe I'll say a little bit of what's written down here, and then I'll show you an example on the computer, and then we'll continue on Wednesday. But saying a little bit about principal component analysis. So one of the reasons why people apply statistics is to identify and quantify relations between variables, i.e. look at like correlation and covariance. And so for a more explicit example, like I think everyone knows what a cryptocurrency is. Maybe when they wrote this book, maybe it was more niche or something like that. But so cryptocurrencies are digital stores of value that are encoded in the blockchain or in a blockchain, which is a system of keeping track of transactions. So like everyone's probably heard of like Bitcoin and Ethereum. Then there's like tens of thousands of other crypto coins or like meme coins or whatever that have various purposes. And so one thing you can use principal component analysis for, I mean, this would kind of be, I mean, it's so complicated, it's probably not going to boil down to like one or three components or anything like that. But using principal component analysis, you can answer questions like whether the entirety of the crypto space operates as a single system, meaning that the value of all coins go up and down together based on a single component, or whether or not there are going to be independent subcategories within that space, meaning that there's some coins or some groups of coins that change independently of one another that ends up influencing the value of all the other coins as well. I mean, you would imagine that Bitcoin probably has like the most influence in terms of like the value of other like coins. So that would mean it would have like a significant contribution to the component. And so we can test this hypothesis by performing a principal component analysis on a data set that contains the prices of various crypto coins over time. And so if the entire crypto market operates as a single entity, then the scree plot, this is kind of a new idea, that I'm introducing now. Well, I mean, I didn't invent it. It's from the book, but we haven't seen it in class is what I'm saying. It's a graph of the eigenvalues of the data set's covariance matrix. It's what's written down here. So each of these dots, the x-axis tells you like the number of components that you have, which is really like the number of columns that you would have in like your U matrix or something like that, or the number of rows you would have in your V matrix. Really the number of eigenvectors you have. Maybe that's what I should be saying. So this number measures the number of eigenvectors you have on the x-axis. And then on the y-axis, it measures the size of the corresponding eigenvalue. So the larger the eigenvalue, the more significance it has in being able to, I guess, replicate the data that you're looking at. So here you can kind of like these smaller values you can kind of shed if you're trying to like reduce the dimensionality. You don't want to consider like every single eigenvector. For this example, you would just really consider this one because all the other ones are close to 0, right? So in understanding just this eigenvector corresponding to this eigenvalue here, you would be able to have a good understanding of what's going on with the data. So all crypto markets in this picture, it would suggest that there's only a single component you have to understand the movement of every single crypto market. Which definitely isn't going to be the case. But you can also say like if there's going to be 3 independent subcategories, that means there's like 3 significant eigenvalues that correspond to components that could be used to approximate your data. So you can take something that's larger dimensional and restrict it to something that's 3-dimensional, and that would give you a good approximation of the data. It's much easier to understand something that's 3-dimensional than it is to understand something that's 9-dimensional. For instance, you can actually plot something that's 3-dimensional. You can do that in 9 dimensions, obviously. Right, so there's a little bit more saying here. I guess before, I don't know, I'm going to stop reading there. I want to show you at least some of the ideas applied, and I'm going to show you this again in class on Wednesday, I guess. I need to log that. So at least showing like what's going on with like the covariance matrix. All right, yeah, so I'll post this on Canvas later on. I made like a little Jupyter file that goes through like a specific example of applying principal component analysis on a data set, where the data set is going to contain time series data from the Istanbul Stock Exchange, not the International Stock Exchange, the Istanbul Stock Exchange here, along with stock exchange data from other countries as well. So I'll go through this in more detail on Wednesday, but I do want to go through some of the code. So the first block or the first cell doesn't really tell you anything. Is this loading various packages that we'll use later on? This cell right here is really doing what I was talking about on the first part of the section 7.3 notes. So first, we're reading in a URL, which corresponds to this Excel sheet right here, which has a bunch of time series data. So every column corresponds to a different stock exchange, even though 2 of them are labeled the same way. I didn't make this table or anything like that. But this is like Istanbul. I think this is like Germany. This is England. This is Japan or something. This is Brazil, EU, so on and so forth. So you can take this table and then you can read it into a matrix. And then define, so this is finding the matrix here. So you're taking the data, writing it into a matrix. And then we're finding the covariance. So we said before that the covariance is just going to be the transpose of your data matrix multiplied by the data matrix. So that's exactly what's going on in this line right here. And then you normalize by dividing by the length of the data. And then you can go and find the correlation matrix as well via this product of diagonal matrices I was talking about before. So here's finding the covariance matrix. And then this is just illustrating that I'm writing out the Excel sheet I had before as a table. And so what I wanted to show is like what the covariance or how to read like the covariance. So you can go through, I plotted like the covariance and the correlation with one another, or sorry, I'm not like speaking very well. I'm distracted. I'm not used to like just showing like a programming. I never showed like programming to a class before. But anyways, this is what it's going to end up looking like. So the correlation is kind of the one that's a little bit nicer in that it's like normalized between -1 and 1, but they're kind of giving you the same information at the end of the day. So like if you see the red here, like on the diagonal, like every variable is going to correlate with itself with a value of 1. So on the diagonal, you see like this red line here, which is just going to be 1. And then amongst the other variables, there probably shouldn't be that much of a correlation with one another. Aside from some instances where you can see, like, if you look at DAX and the EU, the fact that it's red here seems to indicate that changes in EU is going to correspond to changes in DAX. Same with like FTSE in the EU, largely from the fact that this is like European Union, this is Britain, and this is Germany. So whatever happens in the EU is going to probably have some influence with respect to like Germany and England as well. So that's what's going on with like the correlation matrix. And so what we'll do on Wednesday, I'm probably out of time. So this is what the data would look like as a time series. Eventually we'll be doing eigen decomposition on the correlation matrix. And from there, we'll be able to reduce it to something that consists of just like 2 components instead. So I'll show you all of this later on. I'm over time, but this is what we'll do on Wednesday.
We're gonna extra small thing.